Good afternoon, everyone. I am feeling a little unwell, as you saw in the email, so I'm making this video to help teach the concepts that we would have covered in class today without risking getting any of you ill. So hopefully I will be up and back to 100% by Thursday, and we'll meet in class then. All right, so we're going to start out with finishing up the tiny bit we had left on 3.3. So we're going to talk about the fundamental counting principle, and that definition is on the handout that I gave you on Thursday of last week, and that definition is for a multi-stage experiment with n stages. For the first stage has k outcomes, the second stage has k2 outcomes, the third stage has k3 outcomes, and so on. The total number of possible outcomes for the sequence of stages that make up the multi-stage experiment is k1 times k2 times k3 times all the way to kn. All right, so let's look at an example that'll help explain that. So let's see, let me change my drawing utensil here. So, whoa, no, don't want that, never mind. Ignore that. Okay, so example. So let's say we want to determine the number of 5-digit zip codes don't know why I did that, but okay. That can be made from the digits 0 to 9. Okay, and we want to assume that those digits may repeat. All right, so the reason that we use the fundamental counting principle for this particular problem is because in a 5-digit zip code, you can think of it kind of like 5 individual slots. So 1, 2, 3, 4, 5. All right, and for each of these slots, we have a total of 10 options because we're counting 0. So there's 10 options for this one, 10 options for this one, and so on. Each of these has 10 options. So in this situation, like in our definition where it says there are n stages, so these are our n stages, there are 5 of them, and then each stage has k outcomes. So this has 10 options, so 10 possible outcomes, 10 more possible outcomes, 10 more possible outcomes. And the reason this works is because we can repeat. So if we couldn't repeat, then we have to use something else, which is what we'll cover in 4.4. But since we can repeat the numbers, it's all good. There are 10 options for every single one. So according to our definition, if we want to know the total number of possible outcomes, someday I'll be able to write super pretty with this pen, but that's not today. The total number of possible outcomes is going to be the total number of outcomes for step 1, which we said was 10, multiplied by the total number of options for step 2, which we also said was 10, total number of options for step 3, which we said was 10, total number of options for step 4, which we said was 10, and the total number of options for step 5, which we also said was 10. So technically we have 10 to the 5th power, which gives us 100,000. So there are 100,000 5-digit zip codes that can be made from the digits 0 through 9. Oh, and that's what happens there. Okay, all right, so let's look at another example. How many Even 4-digit PIN numbers can be created from the digits 0 through 9. All right, so again, we're going to use the fundamental counting principle because it's like we have 4 spots. Okay, and each of them have a certain number of outcomes. All right, so here, this one's a little different though, because the first number, it can be anything from 0 to 9, right? So there's 10 options there, like in our previous example. In the second spot, it also can be anything from 0 to 9, so there are 10 options. The third number can be anything from 0 to 9, so there are 10 options. But the last number cannot be anything from 0 to 9. It says it has to be even. And we know even numbers end in 0, 2, 4, 6, or 8. So there are actually only 5 options for this last digit. And I'm going to write those options over here so you guys can see it. Our options are 0, 2, 4, 6, or 8. So that means when we're counting the total number of even 4-digit PIN numbers that can be created, we need to take 10 times 10 times 10 times 5. All right, and that comes out to be 5,000. So quite a few. All right, and that is the end of 4.3. So you should be able to complete all of your homework for 4.3. And now we're going to move on to 4.4. All right, so 4.4. I'll have the handout for 4.4 for you guys on Thursday. This section is over combinations and permutations. Okay. All right, but before we can dive into the actual combinations and permutations, we need to talk just for a second about something called factorials, because you have to understand factorials to be able to do the other ones. Factorials are given by using the symbol exclamation point after a number. And what it means is you take that number, let's call this number n. So in factorial, you take n and you multiply it by whatever n is minus 1. And then you subtract another one, so n minus 2. And you just keep multiplying down until you've counted all the way to 1. So we'll look at an example for that. Take the example 1 for 4.4. We want to evaluate 6 factorial. So in this situation, 6 is our n. So 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1. Do not do times 0, because then your whole thing would be 0, and that would be pointless. And so here, that whenever you put that in your calculator, you get 720. If you do not have a graphing calculator yet, get one as soon as possible. This section is where graphing calculators needed to be used. Okay, so I'm going to show you on my graphing calculator how you can do factorials in your calculator, and it's much easier than having to type 6 times 5 times 4 times 3 times 2 times 1 in your calculator. Now you can do that, but it just takes longer. All right, so Let me stop the share so you'll see me again. Okay, so I have my calculator here. This is not an ideal way to show you, but we make it work, I guess. All right, so I want to do 6 factorial. So the first thing I do is I put in 6. Is that a 6? Yes. Okay. Then I go to this math button, and everything is reversed in like, because it's mirror image, but I don't know how to change that, unfortunately. Let's see, is there a way I could change it? Portion of screen. Nope, there's not. So unfortunately, everything else will be backwards. Sorry about that, y'all. But hopefully you can still see it. Then I go all the way over to the thing that says PRB. Then I use my down arrow here to go down to number 4, where I have an exclamation point. And then I go down here and I hit enter. And as you can see, now I have 6 factorial. So then I hit enter again, and I get 720. I'm going to try to find some directions online as well, since it's reversed in my camera, and I can't change that. So hopefully between this video and the directions I find online for you, and also we can go over it again in class on Thursday if you want, hopefully everyone will be able to get it. Okay, so now I'm going to reshare my screen. All right, so now we want to look at another example here. So this is example 2. And this is, we want to evaluate 6 factorial divided by 4 factorial. Okay. So you can do this 2 ways. You can put this whole thing in your calculator, or you can simplify it first. And I'm going to show you both ways. So we know from beforehand 6 factorial. 6 factorial is equal to 6 times 5 times 4 times 3 times 2 times 1. And 4 factorial is equal to 4 times 3 times 2 times 1. All right, so now what we want to do is we want to go and cancel out everything we can. So we see there's a 4 in the numerator and in the denominator. There's a 3 in the numerator and the denominator. There's a 2 in the numerator and a 2 in the denominator. And there's a 1 in the numerator and a 1 in the denominator. So that means after we finish canceling all of those out, all that's left is this 6 times 5 in the numerator, which we know is 30. Okay. All right, now I'm going to show you on my calculator. All right, so first thing I'm going to do is I'm going to put in a 6, and then I'm going to go to math. I'm going to go all the way over to PRB. I'm going to go down to 4. Then I'm going to hit enter. And that's going to make that little exclamation point show up. Then I'm going to go over to divide, which everything's flipped. It's on the other side. Divide by 4. And then I need another factorial symbol. So I'm going to go back to math, over to probability, down to 4, just the exclamation point, hit enter. Now I have 6 factorial divided by 4 factorial. I hit enter again, and I get 30 as my answer, which is good, because if they didn't match, then, well, I would stop this recording, figure out what was going on, and then do it again. That's the good thing about recording. Okay, all right, so let me share my screen again so I can go on to the next example. Okay, so now that you've seen how to do factorials, we're going to talk about a way to determine how many different ways that a certain set can be arranged. So the best way to do that is just by showing you an example. A doctor visits her patients each morning. In how many ways that's supposed to say ways. I don't know what that's supposed to say ways. Can the doctor visit her 8 patients? So how we find this, if you just have a set of things and you're wondering in how many different ways you can order that set of things, all you have to do is take the number of things and apply the factorial to it. So in this case, the number of ways that she can visit her 8 patients is 8 factorial, which is equal to 40,320, which is insanity. I'm going to double check that because that sounds very suspicious. That's really high. Nope, that's all right. Double checked on my calculator. 40,320 ways. All right, so now we're going to talk about combinations. Combinations and permutations. Okay. All right, so on your definition sheet, it says a combination is a selection of objects from a group without regard to their arrangement. And a permutation is a selection of objects from a group where the arrangement is specific. All right, so first I'm going to draw some pictures here. So let's say you have a big set of objects, and I'm just going to put some objects in here. Going to kind of make this look like a pepperoni pizza. Okay, so here's all of our objects. If I go in and I say, I want to know how many different ways can I select 4 of those objects. So I go in and I'm going to select these 4. This is called one combination. And I say, okay, well, I want to go again. So I'm going to go in and I'm going to select these 4. This is another combination. All right, so permutation and combinations, they both work with this idea. You have a set of objects and then you go in and you pull some of them out. The difference between combination and permutation is order matters. So for example, let me go to the next page here. And I'm going to draw a big diagram here. And I'm going to label numbers on them. Okay, so this is our huge, it's not that huge, but it looks kind of huge. Ah, that's what's so close. All right, and I'm going to use circles, but with numbers in them. 1, 2, 3, 4. That's supposed to be a 9. All right, so combinations. So here we have 10 objects, and we want to pull out 3. Choose 3. Okay. Combination says, I'm going to take object, let me use a color here, let's use orange. Combination says, I'm going to choose object 1, 2, and 4. So one of our combinations is 1, 2, and 4. And then combination goes back in a little bit later and says, oh, well now I want 2, 4, and 1. So as you can see, this set of numbers here and this set of numbers here have the exact same numbers in them. They're just in a different order. So whenever you're considering combinations, these are considered equal. Because they have the same elements, even though they're not in the same order, they're considered equal. Whereas if you go over here, permutations are picky. That's how you want to think about it. Oh, I ran out of room. Let me erase. Permutations are picky. They care about the order. So for example, if the first time they go in and they say, I want 3, then 6, then 7. And then a little while later, they decide that they want to draw 7, and then 6, and then 3. So you get the set 7, 6, 3. These two sets are not equal because the order is not the same. Okay. All right, let's work some. Okay, so that's the general idea between combinations and permutations. And so now we're going to work some actual calculations using them. Okay. All right, so your formula for combinations. And then your formula all right, and in this, N is your number of objects total. So N is your number of objects total. R is the number of objects selected. So if we go back and we look at the page before at this picture, there were 10 objects total, so 10 would be our N. And for both of our examples, permutation and combination, we chose 3. So in this example, using the notation for combination, we would have 10, because there's 10 objects total, a big C, which indicates our combination formula, and then the number of objects we chose was 3. Over here for our permutation, number of total objects is 10, a big P to stand for permutation, and we chose 3 objects. All right, so let's evaluate. (5C2). This means that there are 5 total objects, and we want to choose 2 at a time and find out how many different sets of 2 can we choose from a set of 5 objects. So I'm going to rewrite the formula here since it's not on the screen anymore. All right, in this situation, N is 5 and R is 2. So now I'm going to plug that in. When you put that in your calculator, you're going to get 10. But there is an easier way to do it. So I'm going to stop screen sharing to show you the calculator trick. All right, so I want to find 5C2. So the first thing I do in my calculator is I put in the 5, because that's the number in front. Then I go to math, over to probability, down to number 3, hit enter, and then 2. So you see how we have the 5C2 looking thing like we have on the paper? I hit enter, and I get 10. Okay. And we'll do that a couple more times so you'll be able to see it. All right, so now we're going to evaluate a permutation. All right, so this time we're going to use 5 objects, choosing 2 at a time, but we are going to find the permutations. All right, so as a reminder, our formula is n factorial all over n minus r factorial. So in this situation, 5p2 is equal to 5 factorial all over 5 minus 2 factorial, which gives me 5 factorial all over 3 factorial, which gives me 20. So as you can see here, the number of permutations is 20. And the number of combinations was 10. So which type of equation you're using does matter. Okay. All right. So now let's look at some word problems using this idea. You need a password. Nope, never mind. We're going to do that one later. We're not going to do that one first. Let me change my order here. How many ways can Carlos choose 2 pizza toppings from a menu of 6 toppings if each topping is only used once? All right, so here we need to decide, do we need to use our combination formula or our permutation formula? All right, so here, if it's a combination, we need to figure out, we need to be able to show that the order doesn't matter. So we're talking about pizza toppings. So let's pick 2 pizza toppings. Let's say, I'm gonna pick short ones because I'm running out of room. Olives and cheese. All right, so if olives is chosen first and cheese is chosen second, does that create a different pizza than if cheese was chosen first and then olives was chosen second? In general, no. It's all going to mix together. If you're a chef and you're like, yes, that makes a major difference. In math, this math example, it does not. You still are going to have a pizza with olives and cheese. The customer isn't going to send it back and say, this doesn't have this has olives and then cheese, not cheese then olives, okay? All right, so this is going to be, we're going to use our combination equation because the order doesn't matter. All right, so our combination equation again, just to remind you. Is n factorial all over r factorial n minus r factorial. So in this situation, it said that the number of toppings that you could choose from was 6. So n is going to be those 6 toppings. But Carlos only wants 2. So he's choosing them 2 at a time. So r is 2. So now we take these and we plug them into the formula. Oh, that should not be R. Let me change that. I forgot to plug in 2 there. And when you do all of that, you will get 15 combos or combinations. All right, so let me show you again how to do that on your calculator. All right, so we want 6, because there's 6 total options. Go to your math button, go over to PRB, down to NCR, hit enter. We're choosing 2 of those toppings, so hit 2, and then hit enter again, and there you go, you got 15. All right, okay. So now we're gonna look at a different one. All right. Let's say you need a PIN number with 4 digits between 0 and 9. The numbers do not repeat. How many possible PIN numbers are there? All right, so this is super similar to the fundamental counting principle that we talked about before, but the thing is in this example, our numbers cannot repeat. So that's what makes it different than the other. The first examples we did, the numbers could repeat. All right, so now we need to decide if it's a combination or a permutation. We'll put C or P. All right, so does the order matter? Are the PIN numbers, let's just make up 2. So let's say a PIN number is 2136. Is that different than a PIN number that is 2316? Yes, as everyone who goes to the bank knows, if you switch a couple numbers, it will no longer accept it. Those are not the same thing. So since order matters in our outcome, we want to use the permutation formula. All right. So for this one, I'm just going to show you in the calculator, but first we need to determine n. So the total number of options we had for each number was 10, because it said that we could choose a digit between 0 and 9. So n equals 10. And then it says here that we want to have a 4-digit PIN number. So that means we're choosing 4 of those numbers. So we want to calculate 10P4. All right, so I'm going to show you how to do that on your calculator. It works very similarly to the combinations formula. You put in your total number of objects first. Oh, hold on, got to stop the share, got ahead of myself. Okay, put the total number of objects, which is 10, because we have 10 numbers. Go to math, go over to PRB, go down to the NPR, so that's number 2. Hit enter. Put in the number of objects you are selecting at a time, which in this case is 4. And then hit enter again. So you get 5,040. So that's the number of pin numbers that can be made, 4 digits, 0 through 9. 5,040. All right, so now let's look at another example here. A person tosses a coin 13 times. In how many ways can he get 7 heads? All right, so if a person tosses a coin 13 times, in how many ways can he get 7 heads? So for this one, order doesn't matter. We're not talking about passwords, pin numbers, it doesn't matter. So we're going to use our combinations formula. So we have 13 times, so we're looking at 13 total options, big C, and we want to pull 7 of those. The thing that's important to remember is this is not asking the probability of him getting 7 heads when he tosses the coin 13 times. This is saying we already know he has gotten 7 heads, but on which flip did he get those heads? How many different combinations of flips, like flip 1, 4, 6, 7, 8, or flip 2, 6, 9, 11, 12, 13? On what combination of flips will he get those 7 heads? We're trying to figure that out. All right. So when you put that in your calculator or plug it into the formula, then you get 1,716. So that's craziness. That's a lot. All right, okay, so now for our very last example, for it you have to use both the combination and the permutation. No, not permutation, sorry, 2 different permutation. As you can tell, I am sick. My brain's not functioning 100% here. All right, you have to use 2 permutations equations for this. Okay, so I'm going to write the question down. You need a password with 3 letters followed by 3 numbers between 0 and 9. If the characters don't repeat more than once, how many choices do you have for your password? So here, I'm just going to give some examples of what a password would look like that fits this criteria. Oh, let me get these. All right, so you would have like DUK046. You would have, oh, I forgot, 3 followed by 3 even numbers. That's what's wrong. 3 even numbers. I knew I was forgetting something. Another example would be TUS068 or FAC248. All right, and since the letters and numbers, their order matters in passwords, like we talked about before, we know we're going to use the permutation formula. The only difference here is we have to take our password and we have to split it up between the letters and the numbers. All right, so the reason we have to do that is because for the letters, we have 26 options because we have the whole alphabet. Whereas for the numbers, we just have 0 through 9. So you can't just throw all those in the same bucket. It doesn't work like that. All right, so I'm going to draw a line down the middle here and work each side. So we want to find the number of permutations for the 3 letters at the beginning. So in order to do that, we know there are 26 total letters in the English alphabet. So 26 is the number of objects. P, and the number of letters we're choosing is 3. Now we come over here, we do number of permutations for the 3 numbers at the end. We know we said the number is going to be chosen from 0 through 9. So there are 10 total numbers you can choose, and you're going to choose 3 of them. So that means that this permutation problem comes out to be 15,600 options. And over here, you have 60 different options. All right, but those are separately. This is saying that you have 15,600 options for the letter part, and you have 60 options for the permutation part. But we need to find how many options for all of them together. All right, so the way you do that, so we have, let me rewrite those down. We have 15,600, and then 60. So that means, let's say we just pull out one random 3-letter sequence. So let's do PAT. That means PAT can be linked to 60 different number combinations. So let's pick a different one of these letter combinations. A, B, C. That means ABC can be linked to 60 different ones. And let's pick another one, X, Y, Z. This can be linked to 60 different number combinations. So as you can see, each and every one of the 3-letter combinations here can be matched with every single one of those 60 combinations. So what ends up happening is, in order to find the total number, you have to take the number of letter combinations and multiply it by the number of number combinations. So that means the total number is 15,600 times 60, which gives us 936,000 choices for the passwords. All right, well, I hope that was helpful. If you have any questions, we'll go over them in class on Thursday, and I hope you guys have a great evening.